So you need to remember the composition at each level. So for example, here it is percentage iron and percentage carbon. We need to show here percentage iron and percentage carbon. So percentage iron, initially iron is 100%, carbon is 0%. So if you go here, iron is 99%, but we will show only carbon 0.83% at this point. At this point it is 2%, here it is 4%, here it is 6.67 approximate values. These are the percentages of carbon present at. If you want iron, you can subtract from 100. Okay. So now what is this area is called? Here you will get 1 mark questions. This is eutectoid area. Hypo, this one is called hypo. This area is called hyper. Here also hypo, hyper. Eutectoid, eutectoid steels. This is eutectic. Cast iron. So what it explains is, if you have, if any component having more than 2% carbon, then it is called cast iron. So the steel means if it is less than 2% carbon, it is called steels, and if it is less than 0.83% carbon, it is called hypoeutectoid steels. If it is between 0.8 to 2, it is called hypereutectoid steels. Similarly, more than 2% of carbon in any component is called cast iron. It also 2 to 4 means hypoeutectic cast iron, and 4 to above 4 is hypereutectic cast iron. So depending upon the percentage of the carbon, the name of the component varies. So next is alpha iron and cementite. Here it is called ledeburite. This one is gamma plus liquid. This one is liquid. Here it is again ledeburite. Here it is perlite. Here it is ledeburite and perlite. Okay. So point A, I have marked points A, B, C, D. So A is called eutectic point, where eutectic reaction takes place. A is eutectic point or eutectic reaction takes place. What is eutectic reaction? At A, liquid is converting into two solids, solid 1, solid 2. So liquid is converting to solid 1 is gamma and solid 2 is cementite, austenite and cementite. So I will keep gamma and C as cementite. So gamma is called austenite. For notation, C is called cementite. Or iron carbide, Fe3C, or iron carbide. Next, alpha is ferrite. Next one is leduberite, is mixture of leduberite equal to mixture of austenite and cementite. Next one is perlite, is a mixture of ferrite and cementite. That is eutectic reaction A, and which is more important. Similarly, at B eutectoid reaction takes place, where the solid is converting into another two solids. At B, eutectoid reaction takes place. Eutectoid here means solid is converting into solid, another two solids. So solid 1 is gamma austenite, is converting into alpha ferrite and cementite. Similarly, at C, at point C, peritectic reaction takes place. Peritectic reaction takes place. So here peritectic means liquid plus solid converts to another solid. So liquid is, solid is delta, another solid is gamma. So liquid solid converting into another solid, that is called peritectic reaction. So this is about iron carbon equilibrium diagram. If you look at the old gate questions on iron carbon equilibrium diagram, simple questions they will ask, which you can solve easily. So gate 2004, question number 10. Question number 10, gate 2004, ME 2004. The question they asked is the percentage of carbon in grey cast iron is in the range of. So from current carbon equilibrium diagram, percentage of carbon in grey cast iron is in the range of, don't need to keep exactly the same figure, but in the range, he is asking range, whichever option satisfies you can keep. First option is 0.25 to 0.75%. Second option is 1.25 to 1.75. Third option is 3 to 4. Fourth option is 8 to 10. So if you look at the options, grey cast iron have more than 2% carbon. So A and B are not the answers. But maximum percentage is 6.67. So D is not the answer. Answer is C. Like the simple questions they ask in GATE, percentage of carbon and what will happen. And similarly, another question in GATE 2007, question number 5, 2007. The question they asked is, in a particular iron carbon alloy contains less than 0.83% carbon, it is called. So less than 0.83% carbon, what it called? It is called option A, high speed steels. Option B, hypoeutectoid steel. Option C, hypereutectoid steel. Option D, cast iron. If you look at the options, so you need to know less than 0.83%, so it has to be steel only. So cast iron is not the answer. So if it is less than 0.83, that means hypoeutectoid steel. So option B is correct answer. So such type of questions they ask in GATE for 1 mark especially. So this is about iron carbon equilibrium diagram. So next topic is heat treatment. Heat treatment, why do we need to do heat treatment? Heat treatment, the purpose of heat treatment is to improve mechanical properties. To improve mechanical properties. Mechanical properties means what? Strength, hardness, ductility, toughness. To improve our mechanical properties like strength, ductility, toughness, hardness, etc. We do heat treatment. In heat treatment, what we do is, especially we do a heat treatment on steels only. Heat treatment, we heat the material till critical temperature or above critical temperature, depending upon what is our objective, and then cool accordingly. If you want to, there may be like cooling slowly, cool, quenching, and like different types of cooling is there. Depending upon the type of the cooling, the crystal structure will vary, changes, the new component will form. So here first is annealing. One of the simplest method is annealing, is one of the heat treatment process. So object, why do we need to do annealing? Annealing purpose is to relieve internal residual stresses of a material, to relieve internal residual stresses in a component. So annealing is used. Here there are different types of annealing, but all different types is for, like full annealing and process annealing. For a particular process, if you want to relieve the internal residual stresses for different by using different process, that is called process annealing, and spheroidizing, all this, but all the things are same. So what they do is, we have to remember there is one temperature, critical temperature for steels, where if you heat above that it will become austenite, if it is below it is ferrite. So to understand that, we need to draw TTD diagram. So TTD diagram means time temperature transition. Transition means phase transition, solid to liquid, like that, different states. So time temperature transition diagram, TTD diagram. This diagram explains how the each different types of heat treatment takes place. This is called critical temperature, 720 degree centigrade. If you heat above it, austenite will form. If you heat below, then different types of components will form. So what are all those we need to study? First one is here it is perlite, here it is bainite, and this region is called martensite. This one is temperature, and this is time, temperature and transition. That is called TTD diagram. Time temperature transition diagram. So at different temperature it exists in different forms, the component steel. So in annealing, we are heating the metal below the critical temperature and cool it very slowly. So in annealing, heat the component below critical temperature, heat the component to below critical temperature, that means below 723 degrees centigrade. below critical temperature and cool it very slowly, which is also called furnace cooling. Cooling very slowly, it is called furnace cooling, which is also important. Annealing, the objective is to relieve internal residual stresses. Here the crystal structure will be, because we are cooling very slowly, so the crystal structure will be, fine crystal structure will form, so which improves mechanical properties. Ductility increases, internal residual stresses will decrease, internal residual stresses will be removed. So that is a purpose of annealing. Next one is normalizing. So here normalizing, what we do is we heat the material above critical temperature and cool in open air. Heat the material above critical temperature and cool in open air. Instead of furnace cooling, we have to cool here in open air. The structure what you will get is austenite to fine perlite will form. So austenite to, so if you are getting above critical temperature means austenite will form first. So austenite to, while cooling, austenite to fine perlite structure will form. So fine perlite, which increases strength and hardness. So strength and hardness increases, toughness and ductility decreases. Strength and hardness decreases, ductility, strength and hardness increases, sorry. So strength and hardness increases, ductility opposite, ductile toughness decreases. So normalizing. Similarly, there is hardening. Next one is hardening. Instead of cooling in open air, heat the component above critical temperature and cool in, quench it. Hardening is also called quenching. Heat the component, heat the component above critical temperature and quench it. Quench in liquid bath. Heat and quench in liquid oil bath or water depending upon the material. Just sudden cooling. It is also called as sudden cooling, also called as quenching, sudden cooling. Rapid cooling, so different names. So what happens in TT diagram, if you observe, if you heat above critical temperature, so austenite will form. Once austenite forms, if you quench it, so austenite to martensite will form. So martensite is very hard material. Martensite is highly brittle in nature, which is no use for any purpose. So to improve the, to reduce the brittleness and to increase the toughness or ductility, we again do tempering. Tempering is to increase toughness of hardened component. To increase toughness of hardened component. So tempering always we do after hardening. Get question came once, is tempering is always followed by hardening. So to increase toughness of hardened component, what we do is here heat the component below critical temperature and cool in open air. Heat the hardened component below critical temperature and cool in open air. It is called tempering. So conversion is austenite, here it is martensite to trosite and sorbite depending upon higher temperature. Okay. Next one is mar tempering. Mar tempering is also called stepped quenching. Stepped quenching, heat the material above critical temperature and quench till martensite temperature and then cool slowly. The purpose is to avoid quenching cracks. To avoid quenching cracks, heat the material above critical temperature and quench it just above martensite temperature. Quench it to just above martensite temperature, and then again cool it slowly. So here austenite to martensite will form. Next one is austempering. Is also called isothermal quenching. Here instead of heat the material above critical temperature and quench just above the martensite temperature and hold it for a constant temperature. So here austenite to bainite will form. Austenite to bainite. So that is about austempering. Austenite to bainite. So there is one gate question which we have to discuss. Question number 14. Gate 2003, 1 mark question. Hardness of steel greatly improves with annealing, cyaniding, normalizing, tempering. So answer is tempering. Hardness of steel greatly improves with tempering. So if hardness, as we have discussed, after hardening it will metal become brittle. So to decrease the brittleness and to improve the toughness, we do tempering. So hardness of steel improves with tempering. So answer is D. Next question. Question number 13. During heat treatment of steel, hardness of various structures increasing order is. So in TTT diagram, as we observed, martensite has higher hardness, and below that is bainite, below that is perlite. So perlite has lower hardness, and then bainite, then martensite. So that is answer is D. Coarse perlite, fine perlite, and martensite. Martensite will have lost. Next. Question number 12. 2 marks question. Get. So 13th question they asked in ME 2003. Question number 12 is ME 2004. It is a match the following. It's P tempering, Q austempering, or martempering. Looks like all are similar process and characteristics. So one is austenite to bainite. In that process conversion, austenite to martensite, cementite to globular structure, both hardness and brittleness are reduced. Carbon is absorbed into the metal. Fifth option. So answer is, if you look at the tampering means what? To improve the toughness. So decrease the hardness and brittleness. So P4 is the right answer. So P4. So P4 for Q austempering, austenite to martensite or bainite. So in austempering austenite to bainite, so Q1, or in martempering austenite to martensite. So C is the answer. So 2 marks. If you know what is austempering and martempering, what will happen, then you can solve that. These are simple questions which they have asked in GATE. There are other questions in in iron carbon equilibrium diagram only, like at detecting point what will happen and detectoid point what will happen, all these.